Hi everyone, welcome to my channel Physics Classes. Electromagnetic induction is one of the four fundamental phenomena in electrodynamics. The other three are Gauss law in electrostatic and magnetostatic and Ampere's law. The discovery of electromagnetic induction is considered as one of the major discoveries in science. Modern day hydropower plants, automobile braking systems, transformers, microphones, all this works on the principle of electromagnetic induction. So before getting started, if you are new to my channel, please subscribe my channel and press the bell icon. We know that static electric field generates from charged particles. The electric field lines started from positive charges and terminates on negative ones. So for positive charge, the field lines are directed outwards, whereas in case of negative charge, it is directed inwards. So such electric field can be calculated either from Coulomb's law or from Gauss law. Now just imagine what will happen when these charges move in a definite direction. We know that a moving charges constitute a current. When a steady current I passes through a conductor, it generates a magnetic field that encircles the conductor. Such magnetic field can be calculated from Ampere's law or from Biot-Savart's law. So we have seen that steady current can generate a magnetic field. And this leads to many curious pieces and that time to figure out whether is it possible to produce current from magnetic field. So after several unsuccessful attempts by a number of scientists, finally Michael Faraday observed a very unusual phenomena in his lab. He noticed that current can be generated in a coil when the magnetic field through the coil changes with time. The same experiment was carried out by Joseph Henry at United States. So this is a very simple experimental setup used by Michael Faraday. So here coil is wound around the iron ring and connected to a battery. In a similar manner, coil 2 is connected to a galvanometer. Now Faraday observed that at the moment when the switch is closed or open, the galvanometer shows a very strong deflection. On the other hand, when the switch was kept closed, that is when the steady current flows through the coil 1, no deflection on the galvanometer was observed. So Faraday understood that a current on coil 1 produces a magnetic field, and that magnetic field changes at the moment when the switch was closed or open. Only a changing magnetic field produces a current on coil 2, whereas a steady magnetic field does not have any impact on the coil 2. Now before talking about the Faraday's laws, let's have a look on the meaning of surface factor and magnetic flux. The surface factor is a special kind of factor, and any surface can be represented by a surface factor which is normal to the surface and the magnitude of whose is equal to the surface area. So in this figure, A is a surface factor whose magnitude is equal to this area. On the other hand, magnetic flux is defined as the number of magnetic lines of force passing through a surface. So generally magnetic flux is represented by the dot product of the magnetic field B and the surface area A. Now look at this figure. Magnetic field passes through this surface which is normal to the field lines, and so this magnetic field B and the surface factor A is parallel to each other. Therefore, the magnetic flux is simply a product of magnetic field B and the surface factor A. Now, if the magnetic field passes through an inclined surface in such a way that it makes an angle theta with the surface A, then flux can be written as AB cos theta. In general, when the magnetic field is not uniform and the surface is not a flat surface, the magnetic flux can be represented as B dot dA integration over the whole surface, where dA is a small surface element. Okay, let's come back to the Faraday's experiment again. Consider a coil having multiple number of turns which is connected to a galvanometer. Now suppose you try to move a bar magnet towards the coil. As you move the magnets towards the coil, you will observe a deflection on the galvanometer. Similarly, when you move the magnet away from the coil, you will see again a deflection on the galvanometer, but in opposite direction. When you move the magnet towards or away from the coil, magnetic field lines passing through the coil, that is, magnetic flux, changes. A changing magnetic flux induces an electromotive force on the coil, thus produces a current, and eventually you will see a deflection on the galvanometer. More interestingly, the direction of this induced EMF and thus the current depends on the movement of the magnet. Now flux through the coil can be changed in different ways. Look at the diagram. Here the magnetic field lines are towards the plane of the paper. In such magnetic field, if you suddenly change the area of the coil, the magnetic flux will also change and an EMF will induce on the coil. Similarly, if you rotate the coil, an EMF will also induced. So based on his experiment, Faraday proposed two laws known as Faraday's laws of electromagnetic induction. Faraday's first law says that if you change the magnetic field passing through a coil or circuit, an EMF will induce on it. And Faraday's second law says that the magnitude of the induced EMF is proportional to the rate of change of the magnetic flux. That is, the magnitude of the EMF depends how fast you change the magnetic flux and the number of turns on the coil. So here J is the induced EMF and N is the number of turns and d phi dt is the rate of change of flux. So here negative sign comes due to the Lenz's law, which I am going to talk in my next video. So thank you.